Welcome back. So now it's part two of lecture 5, and we are going to work on the fundamental theorems of DFT. Just a reminder, in part one, we provided a few hints as to why the density might be the right function to use to solve our quantum mechanical problem. Now, as I finish the last screencast on this slide here with the Hohenberg-Kohn theorems, I'm going to tell you what are the theorems that are described in this paper, and we are going to prove them as well. So there are two theorems in the Hohenberg-Kohn. So the first theorem is going to be related about why the density is the right function. So we already know that if we know the Hamiltonian and we can solve it and find the wave function, the many-body wave function, we can obtain the density for all the variables, for the density for the problem, from the wave function. We provided the equation of the integral over all the variables but one. I mean, one set for, so 4, for example, the 3x, y, z, and the spin. So we've done that. Okay, we know that. This is quite obvious, and it is defined as a function of the wave function. So the Hamiltonian provide the wave function provide density. That's not a problem. Now, what Hohenberg-Kohn theorems claim is this. It says that for non-degenerate ground states, if we have two different Hamiltonians, they do not have the same density. In other words, there is a one-to-one correspondence between knowing the density and knowing the Hamiltonian. So one density corresponds to one Hamiltonian. So that's actually what's written mathematically in the box there, that the density, if you know the density, it corresponds to one Hamiltonian. That's basically the first Hohenberg-Kohn theorem. So that allows us to get the next equation, if you will. It's not really an equation, there is next relationship, that there is a one-to-one correspondence between the Hamiltonian and the density. So that also means that we can recast the problem completely using the density. And we can define a ground state energy that's a function of the density, where E of n is the expectation value of the Hamiltonian for the density. So that's actually a very, very powerful theorem that provides this. Now, the second Hohenberg-Kohn theorem is basically telling you what you can do with this. So the first theorem tells you there is a one-to-one correspondence with the density, between density and the Hamiltonian, and that there is indeed a functional, the energy that's a functional of the density. Now, the second theorem says this, that this functional of the density will be minimal when the density is the actual ground state density among all possible electron densities. So again, using the same language as I used before when we were doing Hartree-Fock and the variational principle, it means that if you had a way to probe every single possible density ever, all of them, so long as they, of course, have the constraint that we discussed before, so the right constraint on the exchange, but also on the integral, on the normalization of the density. If you were able to probe and sample all of them, the one that yields the lowest energy is the ground state density. And that energy is the energy of the ground state. It's pretty powerful, though that's very nice. So Hohenberg-Kohn theorem gives you an idea that now you can forget the wave function, you can just use density. Okay, these are really the fundamental theorems of density functional theory. We are going to prove them. It's actually a pretty straightforward proof. So what does it mean in practice? It means that the ground state energy can be found by minimizing the energy functional, but there is a caveat. And this is, of course, the major caveat of density functional theory, and this is the next point I'm going to show on the screen, is that even though this is true, even though there is no approximation, it's exactly true, it is no approximation at all, the Hohenberg-Kohn theorem do not provide you a recipe to build that energy functional. So we, in the first part of this lecture, on this first screencast, the previous screencast, we showed the example of the one electron case where we actually built the functional, the energy functional of the density for the energy. In general, you cannot do that. There is no recipe to do that exactly. And so all the approximation density functional theory will be about building that functional. But let me tell you that the progress in defining that functional have been steady or even maybe exponential. And so we get to a point where we have a very good approximation. And how do we know this? Well, we know this because of the amazing success or amazing successes that density functional theory has been at reproducing, or even better, predicting experimental data. But I'm actually kind of jumping the guns here because this is something we'll do in future lectures. Today, let's keep talking about the fundamental of Hohenberg-Kohn theorem. So, um, so we have to use approximate functional. And another thing that sometimes is a little bit forgotten, unfortunately, especially for those who are just using density functional theory as a black box or a tool, is that we have to remember that this is on Hohenberg-Kohn theorem is only correct, is only true for the ground state energy. So basically, if you have a system at equilibrium and it's actually in its ground state, this is the Hohenberg-Kohn theorem applies. So can we use it for excited states? In principle, no. It turns out that we can get information about excited states, and we will see that when we talk about Kohn-Sham. But in principle, no, we cannot. This is not part of the theorem. The theorem does only apply to the ground state. I think it's a good thing to remember a little bit those important aspects, just to not work blindly in the interpretation of the data we have. So the first proof, which is the original proof, really, it's a reductio ad absurdum, which of course means when you have such a proof means that you start from a wrong assumption, from an assumption, and then you prove that it leads to an impossibility. Basically, that shows that indeed the initial assumption was wrong, and then you can make you can draw the consequence of this, that the assumption is wrong. So the proof goes like this. We are going to suppose that there exist two different external potentials, so two different problems, and they both give the same electron density. So just to be clear, that assumption is contrary to Hohenberg-Kohn theorem, right? Hohenberg-Kohn theorem says that if you have two different Hamiltonian, in other words, two different external potential, you must have different density. But we are going to assume that you can have the same density for two different external potential. So this is the idea of the proof, right? We start from that assumption. We show that it leads to an impossibility. Therefore, the assumption is wrong. That's the idea. Now, using those two external potential, we define two Hamiltonian, H and H prime, which are built from V external and V prime external. And of course, they have the same ground state density according to the initial assumption. But they do have different ground state wave function. Because the two different Hamiltonian will yield two different wave functions, right? So the wave function, the ground state wave function will be psi and psi prime, respectively. How do we get them? Well, we get them by using the variational principle, and they correspond to the expectation value of the respective Hamiltonian for that state. So this is what I wrote here in orange between the parentheses. So the ground state energy for Hamiltonian H is E naught for ground state wave function psi, and the ground state wave function for H prime is psi prime and gives energy E naught prime, right? So far, so good. That's what we've seen in the first four lectures. It shouldn't be difficult at this point. Now we are going to use a variational principle. Now here's the key thing. So there are two key parts in this proof, and this is the first one. Imagine that you take the wave function psi prime. Clearly, psi prime is not the ground state wave function of the Hamiltonian H, right? Since psi and psi prime are different, we do not have the degenerate state. So therefore, those two states psi and psi prime are different, and psi prime, and this is this equation here, and you have to start from the left. If I look at the expectation value of the Hamiltonian H for psi prime, clearly this is not the ground state. Therefore, that expectation value has to be larger than ground state. That's the first inequality I have on the left-hand side. And then I can expand H. I can say H is H prime plus H minus H prime, right? That's what I've done for the first equality there. Now, the first term, the expectation value of H prime for the ground state wave function psi prime of H prime is E naught prime by definition. And then the last part on this equation simply allows you to write H minus H prime is equal to V external minus V prime external, because of course the other p's are universal, so they are the same for the two Hamiltonian, and the difference between the two is V external minus V prime external. Okay. Now you will also remember that last expectation value, as we have seen many times, and I will actually prove it again in a couple of slides, only depends on the density, right? The expectation value of the external potential only depends on the density. Therefore, the rightmost expectation value only depends on the density, which is the same for psi and psi prime. That's what we started from the assumption. Now we can write the same equation, starting exactly the same equation, but this time calculating the expectation value of H prime for wave function psi. So this is exact same equation as before. But we basically apply it to H prime instead of applying to H. Then we have those two equations, okay? So now what we see, and this is the important piece, I want you to focus on the orange box. The right-hand side, after the plus for the two lines, they are the same modulo a minus sign. Why? Because as I just told you, the expectation value of the external potential only depends on the density, right? We've seen that, and I remind you again, as I said in a couple of slides. So therefore, those two terms, they are the same. I mean, the two terms after the plus sign, they are the same with a minus, with one being the negative of the other one. Now, if we sum the two equations that I have there, on the leftmost, we have E0 plus E0 prime, and on the right, we have E0 prime plus E0. Now, we find that we have a strict inequality, a strict smaller than, because we suppose that the ground state are not degenerate. Of course, this is impossible. I mean, E naught plus E naught prime smaller than E naught prime plus E naught, that's impossible. Therefore, because we find an impossible result at the end, we see that the assumption we started with was wrong. So the assumption that two different external potential yield the same density is not possible. It's never possible. In other words, if you have two different external potential, in other words, two different Hamiltonian, you must have two different densities, which is exactly the first, which is exactly the Hohenberg-Kohn theorem. Okay, so that's what I write here in particular. That's what I rewrite here on this slide. So what I just told you is what's written on the slide. On top of that, you can define, of course, the now that the problem only depends on density. You can write a functional of the density, the energy, which is the energy functional of the density, and this is the second part of the Hamiltonian, the second part of the Hohenberg-Kohn theorem. So we've proved it. Now we've proved it for non-degenerate state, and also we suppose that we had the state that corresponded to a potential. I'm going to provide you a separate proof, which historically is a stronger proof because it's more general, in just a second, and it's equally simple proof. If it's the first time you see this proof, which is likely if you follow this course, I recommend pausing and spending a couple of minutes to convince yourself. Now, I just want to go back, just in case you're not convinced, that the energy that corresponds to the external potential is given by the equation in blue. So this is indeed an equation that we have seen so many times already in Hartree-Fock, but it's just to to repeat and to remind you that um, the energy corresponding on external potential only depends on the density. Therefore, that's why we could actually show that the two equations in the orange box, the right part of the equation, the orange box, were the same modulo a minus sign. So I provide you the proof of, again, here we've done it before, but I provide it here so you can pause the screencast to convince yourself if you forgot. But it's basically what it demonstrates, and it's important. That's also important when we look at the proof number 2, which is essentially an alternate proof, which is, as I said, a little bit stronger, and it's related to it is usually called the Levy's constrained search, and I will explain to you what we mean by constrained search in a second. That paper was published in 1979, so quite a bit after the original Hohenberg-Kohn theorem. But this is an interesting proof to do as well. So basically, it is not a reductio ad absurdum approach. It's a different one. So we know that the ground state energy can be found by minimizing the expectation value of the Hamiltonian for all the wave function psi, so long as they're normalized and anti-symmetric. I keep saying this to you. So you can find this. This is an equation we've seen a number of times in Hartree-Fock. Now, we can actually decide to constrain our search. And this is exactly where the name Levy's constraint search comes from. And we do it in 2 steps, okay? Now, we are going to suppose that we have a given density, whatever it is, a certain density which is, of course, obeying the fact that you have n electrons. So it has to integrate to n electrons. And we are going to consider all the densities. And we are going to work, if you will, in the subspace of a given density n. And what we are going to do in that case, we are going to minimize the expectation value of the Hamiltonian for those wave functions that yield the density n, right? So I can do that. I obtain the equation there, the last equation I show on the screen, and I could separate. I could actually put the part of the external potential outside, because, of course, that one is not going to change. For a given density, the integral over VR and R is always the same. You can pick other wave function that will yield the same density. That part will always be the same, right? The last part. So it's not going to be part of the minimization. It's a constant, if you will. Now, so exactly what I just showed you a second ago. Now, we can define a functional f of n, which will just be the kinetic energy plus the electron interaction. And that functional, of course, is a functional of the density, right? It's going to be the minimal expectation value of T plus VE for a given density. And we are going to search all the wave functions that yield that density, right? So this is what we have this, and we can define that functional of the density, which is, of course, obtained by that wave function that yield the smaller expectation value. That's why I call it psi with a label min. So in the next slide, we are going to restart from that equation. This is here, that equation. Now what we can do is that we can decide to minimize that functional f of n for all the densities, right? So if we minimize that wave function of n for all the densities that yield n electrons, again, this is a constraint, always that constraint that we have, we find that that energy is going to be obtained by minimizing all over all the densities for the energy, which is f of n plus the integral, of course, that really correspond to the external potential. So essentially what we just wrote here, because we are looking at every possible density that yield n electrons, and we are looking at all the wave function for each of those densities, we know that this minimization problem is equivalent to the minimization problem that we had in the in Hartree-Fock, for example, in the Rayleigh-Ritz variational principle. actually not just in Hartree-Fock, because Hartree-Fock is approximated, but in the general problem that we solved. And basically, what we just demonstrated the problem that we just proved the Hohenberg-Kohn theorem that basically tells you that you can write things in terms of the density. That's basically what it is. Now, what's nice about this is that you do not. It's okay if you have a degenerate ground state, and that happens quite often, of course, to a degenerate ground state. And even better, we are actually now doing the search over densities that are called n-representable. So n-representable means that density that can yield n electrons, which is actually a easier thing to do than what we did before, because before we were doing the density that corresponds to a potential. So that's basically prove the Hohenberg-Kohn theorem again. This is actually a pretty simple proof now that we have done all the work in the first 4 lectures. That was kind of the pedagogical reason why I spent so much time working with all those variables and all those operators. It's going to come very handy as we move forward too. Now, again, in one of the reference that I provided you at the beginning of this course in lecture 0, there was also a mention of a strong form of Hohenberg-Kohn theorem, and this is in this paper, which is actually more recent in 2004. And actually, it's interesting to look at it. The proof is provided in details in that paper. It's actually quite it's fairly easy to follow the proof that there is in that paper. And that paper is sometimes that equation is a result which I'm not going to prove, but the idea here is that it's called a strong form because you get a little bit more information here. Basically, the delta V is a change in the external potential, and delta N is how the density changes when you change the potential. So one thing that you can, if you agree with that equation, or if you accept it, or if you can prove it by looking at the paper, you can see that if there is a variation in the potential, so a delta V that's not equal to 0, delta N must be different from 0, because the integral has to be strictly non-zero. So that means, of course, that the only way to have a density that doesn't change is to make sure that everything works together. So we see that well in that equation. So that also means that a change in potential must change the density, and the Hohenberg-Kohn theorem, of course, can be proven for a single variable that says it cannot be 2 local potential with the same ground state charge density. That's for historical reason, and also for additional information. This proof of it is interesting. Don't want you to lose track to the fact of what matters is to understand the Hohenberg-Kohn theorem and the consequences. The proofs are useful to really test our knowledge of the different variables and different moving parts. So another thing is that we can also learn from this equation is that if we have more repulsion, so delta V is positive, so we add more energy to the problem, so it's repulsive, then we have the density has to go down. So that's also makes sense. So this is not something that we directly have in the 2 other proofs that I provided you for the Hohenberg-Kohn theorem. So that's why we call it strong, because it has more information than them. Okay. Now, the next few slides are going to be important because these are comments on the Hohenberg-Kohn theorem and how to understand them. So there are a number of comments. There are going to be a lot of repeats of what I told you, but these are the take-home messages from this screencast, really. So a non-degenerate ground state wave function is unique functional of the ground state density. So that's basically what it means. What we saw is that the density corresponds to a given Hamiltonian, but a given Hamiltonian provide a given, or in principle, a given ground state psi 0. I say in principle because we cannot always calculate it, but we know it exists. And therefore, since density yields the Hamiltonian and the Hamiltonian yields the wave function, the density yields the wave function itself. So we can write that the wave function is a functional of the density, the ground state density. So that means that we can also apply this to any expectation values, because the expectation values, which are the operators corresponding to 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 information we can measure, which are usually written in terms of the wave function, of course. But since the wave function is a function of the density, we can see that the observable are also function of the density. So that really brings that goes beyond the energy being a function of the density. Now, a second comment we can make is that one of the observable, of course, is the energy, and we've seen this before. This is basically part of the second theorem of Hohenberg-Kohn theorem. And we see that if we try all the density, we can always find kind of some sort of variational principle, which is now for the density instead of the wave function, that the ground state density will be the one that corresponds to the lowest energy. Okay, so that also mean that even if we have an approximate value, an approximate solution for the density, we have an upper bound of the energy. That's really what it means. So we mean that the energy, whatever energy you obtain from a trial, from an approximate density, will be an upper bound to the actual energy. So that's a useful thing to do in practice. So more comment that we have is that in general, we actually have to provide also a constraint on the number of electrons. Again, with a Lagrange multiplier when we try to minimize EV. By the way, the V corresponds to a given external potential, since the problem is defined for a given potential, external potential. So we need to minimize not just EV, but also EV minus mu n, where mu is a Lagrange multiplier, n is the number of electrons. So we do that in order to make sure that we have a constraint search with indeed n electrons. So that means that when we calculate the functional derivative, we want the functional derivative to be equal to 0, and that gives us this answer here. So the second equality, I'm going to prove it to you in a second. It's basically saying that, yes, of course, the functional derivative of EV with respect to density is equal to mu, but mu itself is equal to the usual partial derivatives of the energy with respect to the number of electrons. So this is basically the definition of the chemical potential. Chemical potential is the energy you need to is the additional energy you have when you change the number of particles in your problem. So if you add an electron, the chemical potential will be that energy that you need to add that electron. So that's basically how you read the second equality. So let's prove this. I think it's again another application of the functional derivative, which is nice. So let's calculate the partial derivative of E with respect to n. And now we can mix the functional derivative into the game, and we find that just basically like where we have in calculus, we find this chain, if you will, this chain derivation. So we have the same derivation rules. The only difference from what you've done before in regular calculus is that you need to integrate over all the position in space, of course. But that's the main difference we have here. Now we can calculate the various value. In the previous slide, we saw that the functional derivative of E with respect to n was equal to mu. So we can write this from the previous slide. And what's nice is that the integral does not depend on n itself. So we can bring the partial derivative outside of the integral and mu outside of the integral as well. So we end up with this equation. And of course, the integral of the density over all space is equal to the number of particles, is equal to n, right? It's the integral of the entire density. And then we end up with a partial derivative of n with respect to n, which is 1. And therefore, this is equal to mu. So this is to prove you that indeed everything seems to make sense, and we get really this idea that mu is the chemical potential. Okay, so it's time to have more comments on the Hohenberg-Kohn theorem. Um, so we know that we have we can always write things like this, and we've done this before, but even in this screencast, that the energy is made up of three terms: the kinetic energy, the electron energy that's written by the letter U, and then the external energy due to the external potential V. However, the first two parts, T and U, are universal functional, right? That we've seen that many. This do not depend on the problem. Therefore, we usually bunch them together and write them F, just like I did in the Levy's constraint search. And so this is the way you usually write this. Um, T and U are not dependent on V, as I just told you. And finally, for the maybe hundredth time, the the functional of the external potential, so that functional is obtained, so that energy, part of the energy due to the external potential, is indeed dependent on V, and is a local functional as written here. And we have seen this. And obviously this is not universal because it depends on the external potential. So that's really nice. So just to end on something that, just to wrap this up as the last slide of this screencast, we now have a variational principle for that total energy functional that I just defined, uh, with the constraint of the number of electrons being constant. That's why the mu is there. You will note that in previous slides, instead of writing the integral over the space of Ni, I put capital N, which is of course the same thing. And we end up having to solve that variational problem. So if we could try every density that has n electrons, we'll find that for the ground state, that equation, that variational equation, will yield um, the correct energy and the correct density. And on top of that, the the chemical potential is identified with the Fermi energy at T equal 0 Kelvin. And this is one thing I'm going to say, and it's going to really wrap up this lecture, is that this is the first time I talk about temperature. I've not spoken about temperature at all since we started this course. Turns out that density functional theory is indeed a 0 Kelvin theory. So there is no temperature. We work all at 0 Kelvin, and this is something that we are going to analyze and explore way more in the future lectures. I thank you very much for staying this long in this screencast, and I hope you learned something. Thank you.